Hi, this is Mark Berkey, and in this video I'm going to explain how you can calculate optimal mixed strategies. In my book on game theory called Anticipating Reactions for Winning Actions, I mentioned a few times about mixed strategies, but I didn't go into actually how to calculate them because it can be a little bit complicated to think about. But if you're interested, here's a video where we're going to go through calculating a mixed strategy equilibrium, and I'm going to try to give you an intuition about why what we're doing makes sense. It's hard for most people to understand this. It's pretty complicated, but let's give it a try here. Let's suppose we had the following game where there are two players, society and a potential criminal, someone who might want to steal something. But might not want to steal something given the right conditions or the wrong conditions. So here's society. Society's payoffs are in bold and their choices are in bold. Society can either put the expense to put cops on the street or no cops on the street. Or you could think about this instead of society, maybe it's the mayor of a town or the leader of a town. And here's the criminal. They can either steal things or not steal things. If there are cops on the street and the criminal steals, he's going to get caught. So in this case, there's a decent payoff for society because we spent the money to put the cops out there and we caught the criminal. This is not a good deal for the criminal if they steal when there are cops out because they're going to get caught and be punished. If society puts cops out and criminals don't do anything, then they might be criticized for putting out the cops and spending the money, but they didn't catch anyone. So this seems like they did the wrong thing. So bad payoff for society, kind of a medium neutral payoff for the criminal. If the criminal doesn't steal, they get one whether there are cops or there are no cops. They get one either way. Maybe they just go to work and they earn a small wage of 1 when they don't steal. Or when the criminal steals, he gets -2 when he gets caught. He gets 5 when there are no cops because he doesn't get caught, and he gets to sell whatever he stole. Now, society, when they don't put cops out and the criminal steals, they look bad, so they get a 0. If there are no cops and no one steals anything, society gets a large payoff of 7. We didn't have to spend the money for the cops, and there's no crime. It's the best of all possible worlds, so that's a very good payoff for society, a 7. So, let's check this game for pure strategy Nash equilibrium. And to do that, well, let's look at the best response of society when the criminals steal, and that's to put cops out, right? So we could highlight this. So let me instead of underlining like I do sometimes, let's highlight the 2. That means that the best response when the criminal steals is to put cops out. The best response when the criminal doesn't steal is to not put any cops out. Okay? Let's look at the best response of the criminal to the actions of society. If they put cops out, then the best response is not to steal. So let me highlight that. When there are no cops on the street, the best response of the criminals is to steal. Okay, so there's no Nash equilibrium here in pure strategies. John Nash showed as part of his work that there's always going to be a Nash equilibrium in mixed strategies. If there's not one in pure strategies, there will at least be a mixed strategy equilibrium. A mixed strategy equilibrium means that society is going to randomize. They will sometimes have cops out and sometimes not have cops out. And the criminal sometimes will steal and sometimes will not steal. So what we want to do is calculate the probabilities that society will put cops out and criminals will steal. What are those 2 probabilities that they will or won't steal or will or will not put out cops to where it's a Nash equilibrium? So, well, what does that mean, Nash equilibrium? Well, let's read our my standard definition of a Nash equilibrium. An equilibrium is if we can find an outcome where neither player would want to change their decision after learning of the outcome. In other words, each player has made the best response to the other player's choice. Now with a mixed strategy, we have to change this idea a little bit, and here we're talking about probabilities, not really an outcome. So let's call something equilibrium probabilities, right? There's not really a choice. Probabilities. Equilibrium probabilities, it's not really an outcome. If we can find probabilities where neither player would want to change their decision. What kind of decision are we talking about? Well, they're not going to change their probabilities, right? After learning of the outcome or decision. Either way, there are a few different ways you can think about this problem and a few different ways you can actually solve this problem. You get the same answer either way. So neither player would want to change their probabilities after learning of the outcome. Now outcome, again, here we mean after learning of the other player's probabilities. See, I told you this is a little hard to think about. In other words, each player has made the best response to the other player's, not really choice, but choice of probabilities. Okay? How are we going to do this? Well, here's another way to think about the idea of what we're doing here. We want to let's take the position of society, or the mayor, or the police captain, or whoever here. What he wants to do is choose a probability of patrolling the area so that the criminals will be indifferent between stealing or not. Why does this make sense? Why does this have to be part of this Nash equilibrium and probabilities? Because only by choosing this particular probability that we're talking about here, this probability of patrolling the area to make the criminals indifferent, if the criminals aren't indifferent between stealing or not stealing, then the criminals will not be willing to roll the dice to make a mixed equilibrium. Let me try to say that again in a slightly different way. There's only going to be one probability here. Let me highlight these words. There's only going to be one probability. Maybe it's 40%. We're going to find it. But maybe it's the probability is 40% that if they send cops out 40% of the time, and they don't send cops out 60% of the time, there's going to be one unique probability that will make the criminal say, well, you know, I'm indifferent between going and stealing today and not stealing. Therefore, let me just roll the dice to decide whether I should steal, right? All other probabilities, if the cops patrol more than a certain probability, say 40%, it's not, but we'll see what it is in a second. If the cops patrol more than this probability, the criminal will never steal. Less than this probability, he will always steal. So there's some probability we're going to find that makes the criminal indifferent between stealing or not, so he's willing to randomize. Says, let me just roll the dice. Now, on the other hand, on the flip side, there's going to be a probability, though, that the criminal randomizes with respect to. If the criminal is going to steal more often than this, then the police commissioner will always put cops out. It's basically tantamount to this. Look, if this is difficult to explain, I'm doing the best I can. If society knows for sure the criminal's going to steal, what will society do? Put cops out. If society knows for sure the criminal's not going to steal, what'll they do? They'll not put cops out, right? So if the criminal puts this probability equals 1, he's not going to steal. And this probability, therefore, must be equal 0, right? If he's not going to steal, and he's, so we're over in this column, society has one choice they're going to make. The higher the probability is of not stealing, the better, the more likely it is that society doesn't want to put cops out, okay? So let's go ahead and solve for these two probabilities, and then we'll talk about them and try to interpret why these make sense. This is why most people don't teach this probabilistic method. It takes a lot of talking about. Okay, let me set up an equation here that embodies what we're talking about right here. We want to choose a probability. This is the police commissioner. So the cops want to choose the probability of sending cops out. Let's just call that PC, probability of sending cops out, to make the criminals indifferent, right? So we're going to make the criminals indifferent. Let me highlight that. How can we do that mathematically? Well, what we want to do is write down the payoffs here. When the criminal steals, okay, let's get rid of these probabilities here just for a second. When the criminal steals, what is their payoff going to be? Well, there are two different things the criminals could get. Either -2. When do they get -2? When the cops are out. Or they get 5 when the cops aren't out. But we're looking at a probability, right? So both of these things could happen with some probability. So probability that the cops are out, PC. Just think about that as 30% if you want to. If you're not used to seeing these kinds of things. All right, let's just put a number there as a placeholder for a second. Let's suppose it's 30% or 0.3, okay? But I'm going to call it PC in general. There's a 30% chance that the cops patrol. If the cops patrol, what does he get when he steals? -2. -2. Okay, so that's 0.3 times -2. But we're just going to call it some general probability of the cops being there here. Plus, well, if the cops are out 30% of the time, they're not going to be out 70% of the time, right? So 30% of the time, this criminal will get -2 when he steals. But 70% of the time, 0.7, he's going to get what? 5, right? So 70% of the time when there's no cops, he gets 5. 30% of the time, he's going to get -2 when there are cops there. So 1 minus PC, this is the other 70% of the time, right? He's going to get 5. But we don't know that 0.3 and 0.7 are the right answers. I'm just putting that up there so that you can kind of see what we're talking about. So what we've done here is we've talked about the case when the criminal steals. That's his payoff on the left. And it depends on the probability they put the cops out there, right? But what we want to do is set that equal to the payoff for not stealing. Okay, so what's that payoff going to be? Well, it depends on the probability the cops put out there. Actually, it doesn't, because he gets 1 either way, right? When he doesn't steal, the criminal gets 1. When there are cops out, he gets 1. When there are no cops out. So really, he gets 1 when he doesn't steal. He's guaranteed to get 1 that way. Now, what if it wasn't 1 either way? Well, what we would want to do is set this up a little bit more complicated way to build in the probability the cops are out there. Let's do that. Well, the probability the cops are out there times 1 plus 1 minus the probability the cops are out there. The other percentage of the time, well, but he gets 1 there also, right? Times 1. So let me put little time signs in between here. Okay. So this is the equation we're solving if we want the criminal to be indifferent between stealing and not stealing. The payoff from stealing, right here, has to be equal to the payoff of not stealing. And that's what we've written mathematically here. And all this just simplifies down to being 1. I just wrote it out the long way. Okay, so if we want the criminal to be indifferent between stealing and not stealing, what is the probability we should patrol with cops? Well, it's just going to be minus 2 times that probability, minus 2 times the probability we send the cops out, plus, let's simplify this. 1 minus PC times 5, well, that's going to be 5 minus 5 times PC equals, and again, everything over here simplifies to 1 because he's guaranteed to get 1 when he's not stealing. I just wrote that out the long way in case you see a problem where these two payoffs aren't both 1. That's the way you would do it. So let's simplify this, and it'll just tell us what the probability we should send the cops out will be. And so this is going to simplify down to minus 7 PC plus 5 equals 1. And then solve that equation for the probability of sending the cops out. And I get something like the probability of the cops should be sent out equals 4/7, or 0.5714 roughly. Okay, so if you want to find this mixed strategy equilibrium, one requirement of it being a Nash equilibrium is that the criminal has to be indifferent. I know this seems weird. The criminal has to be indifferent between stealing and not stealing. If you want them to be indifferent, send a patrol car out 57% of the time. Now, what if you don't want the criminal to be indifferent? What if you want to force him never to steal? Okay, all you have to do is send out a patrol car more than 57.14% of the time. Send it out 58% of the time, 60% of the time, 70% of the time, 80% of the time, or all of the time, right? What we found here is if you want the criminal to be indifferent, send out the cops more than that. If you want the criminal to steal, if you want his optimal decision to be stealing, send out the police less than 57% of the time. If you want him never to steal, send out the cops more than 57.14% of the time. Now let's see why that makes sense real quick. Let's just put some numbers back into this equation that we're looking at right here, and let me just demonstrate this. He's guaranteed to get 1 from not stealing, right? So all we have to do to guarantee that not stealing is his best choice, he can get 1, is to make his expected value of stealing less than 1. So you have to send out the cops often enough so that this minus 2 weighs more, right, than the 5. So let me just demonstrate here that what I just said is true. Let's suppose we send out cops 60% of the time. Let's see what happens in this equation right here. 0.6 times, right, we're just sending the probability of sending the cops out is 0.6 times minus 2, he gets caught 60% of the time, plus 1 minus PC, well that's the other 40% of the time the cops aren't there, times 5. What do we get there? Well, that's negative 1.2 plus 2 equals 0.8. 0.8. That's his expected payoff his average payoff from going out and stealing every day when the cops are out there 60% of the time. His average payoff is going to be 0.8. Well, should he go steal then? No, he shouldn't do that if his expected payoff is 0.8, because he can guarantee himself 1 all the time, whether there are cops out or not, by not stealing, right? So anytime the cops are out more than 60% of the time, don't steal. I know I'm beating this to death, but I want to make sure you're clear on what this 0.7514 means. If you plug in any number less than that, say 0.2, 0.3, 0.1, then his payoff from stealing here is going to be bigger than that 1 that he's guaranteed from not stealing, and he'll steal. Okay? So this is part of the solution. Is in this mixed strategy equilibrium, if the cops act with probabilities and the criminals act with probabilities, the cops will patrol 57.14% of the time. What about the criminals? What is his mixed strategy equilibrium part? Well, okay, well here's the idea. The criminals, if they're going to be a part of this mixed strategy probabilistic equilibrium, then they're going to have to, what's the optimal response, basically, if the cops patrol exactly this often? Well, the optimal response is actually anything. Why? Well, because the criminals are indifferent. So if the optimal response is anything, either stealing or not stealing, another optimal response is to roll the dice or, randomize. Well, if you're going to randomize, how should you randomize? Well, you have to randomize in such a way, if you're a criminal, that not the criminals this time, but the cops or society, so that society is indifferent between patrolling with cops or not patrolling. Okay, so how do we set up this equation? Well, if this is very weird logic, I know, but if you're the criminal, all right, so you want to make the cops indifferent between patrolling or not patrolling. And so we have to set up the payoff function for the cops. What do the cops get when they patrol? Okay, well let me move this down so that we can see. I'll move this to the bottom so that we can see our payoff table here. When the cops patrol, we're on the top row. And the cops are either going to get 2 when the criminal steals or -1 when he doesn't steal. So, what society gets when they patrol depends on the probability that the criminal steals or doesn't steal. So let's call that PS. So the cops will get 2 times. They're going to get that with a probability that the probability that the criminal steals, plus they'll get a -1 times. They'll get that as often as the criminal doesn't steal. So probability that the criminal doesn't steal. Or we can say that a different way. 1 minus the probability they steal. That payoff of patrolling has to be equal to the payoff of not patrolling. So let's set it up. What's the payoff of not patrolling? Well, that's going to be somewhere in the bottom row. And it's going to, again, depend on the probability the criminal steals or doesn't steal. If the criminal steals, we get 0. So that payoff is going to be 0 times the probability the criminal steals plus 7. We get 7 when the criminal doesn't steal. So that's 1 minus the probability. 1 minus the probability the criminal steals. That's the probability he doesn't steal. So we have to set these two things equal. If it's going to be a situation where the cops are indifferent between patrolling and not patrolling. So let's solve this for what is that probability that the criminal needs to steal. So 2 times the probability of stealing plus, or minus 1. So minus 1, let's just distribute that out. Minus 1 times 1 and minus 1 times minus PS. Okay, so we get 2 PS minus 1 plus PS on the left equals 0, and that's 7 minus 7 PS. All right, let's just keep simplifying here. So we get 2 PS plus 1 PS, that's 3 PS, minus 1 equals 7 minus 7 PS. And let's simplify this, and I'm going to get something like 10 PS on the left. And I'm going to add 1 to both sides, equals 8. And so what is the probability that I should steal if I want the cops to be indifferent between patrolling and not patrolling my neighborhood? It's going to be equal to 8/10. So let me just do that here. So the PS equals 0.8. So if the criminal rolls a probability die of some kind and it tells him he should steal 80% of the time and not steal 20% of the time, then the cops will be indifferent between patrolling and not patrolling. And on the other hand, if we found it was 4/7 probability, so the probability that the cops patrol should be equal to 4/7. That if the cops patrol 4/7 of the time and they don't patrol the other 3/7% of the time, then the criminals will be indifferent between stealing and not stealing. This is the mixed strategy equilibrium, where if the cops patrol 80% of the time and the criminals steal, oh sorry, I got that backwards. The criminals steal 80% of the time and the cops patrol 4/7 of the time. That is the mixed strategy Nash equilibrium. Mixed strategy Nash equilibrium, MSNE. And these two probabilities are a best response to each other, in the sense that if they both choose these probabilities, there's no reason for either party to change the probabilities. That's what we mean by mixed strategy Nash equilibrium. A Nash equilibrium is a place where there's no reason to change your mind given the choice of the other player. So this pair of probabilities tells us the probabilities with which neither player has any reason to change their mind. They can't make a better decision than that pair of probabilities. Now, again, it's a little weird to think about. The logic is a bit strained, but it does make a kind of sense if you think about it. Now, there's also a way of solving these problems using calculus, but I think that this way, as difficult as it is, this is a little bit more intuitive, a little bit easier way to think about it than the standard way that most people teach it using calculus. So I hope that by seeing this example, you have a little bit of an idea about what a mixed strategy Nash equilibrium is, and I've shown you how you can solve for these optimal mixing probabilities. I'll try in the near future to make another video with a totally different example to go through this again, and hopefully after you see this done twice, you will have mastered the concept of the mixed strategy Nash equilibrium. This is Mark Berkey. Good luck with your studies in game theory, and I hope that this has been informative.